We're about to start panel 2, Agents for Chemical Reactivity. My name is Dunstan McCauley. I'm the moderator for this panel. Our panelists for this panel are Dr. Jonathan Williams with the Max Planck Institute for Chemistry, Dr. Rachel Adams, Indoor Air Quality Section, Environmental Health Lab of the California Department of Health, and research scientist at the University of California at Berkeley, and Dr. Barbara Turpin, who is a professor and chair of environmental sciences and engineering at the University of North Carolina at Chapel Hill. Our first presenter is Dr. Jonathan Williams.
Thank you very much, and good morning. Yes, today I'm going to be talking now about people chemistry. And just to set that a little bit in context, we heard this morning from Alan and from Richard and from Nina that the indoor environment contains a sort of huge array of complex and very diverse sources. So, for example, cooking, and cleaning, and also the emissions from these various furnishings. And what that means is that trying to get a general impression of the indoor chemistry of the home is very complicated because it can vary very much from one place to the next. So now what we're going to do is we're going to turn our attention to the one common element in all living spaces, and that is the person. Okay? And we're going to ask ourselves the question, what do people emit into this cocktail of chemicals on their breath or on their skin? Or in other words, what are you right now and I emitting into this auditorium for everyone else to breathe? Okay, so we're going to look at that. And here's some examples of people doing exactly that. Okay. So my group got into this line of inquiry through some very unusual measurements that we did in our local movie theater. And it turns out that a movie theater is an excellent piece of scientific equipment to measure the emissions from people. The reason for that is you get a large group of people, so you get an average sample of 250 folks watching a movie, and while they're watching the movie, you pass fresh air from outside under the seats and out through the people and then out through the ceiling, out through a ventilation shaft. And what that means is that anything that the people are emitting, it's basically a box full of people that's flushed with air, anything that they emit can be measured downstream using some of the highly sensitive equipment that Alan was also demonstrating earlier on. So we were measuring CO2, as you know, major gas in your breath, and also a huge number, so several hundred of these volatile organic compounds, some of which you saw again earlier on today. And so what we did was what we found, because our instrumentation is rather sensitive and measures continuously, you can pick up on very subtle changes in the gas phase composition that's caused by people reacting to various scenes in the films. Okay? And this film, as you can probably identify from the peaks, right, is The Hunger Games 2, and you see that when this film is shown to multiple audiences multiple times, there's a certain reproducibility. So you start to see peaks happening in the same places. That's for CO2. So you can see people getting excited or not excited. We also, because of the hundreds of chemicals that we had at hand, we were also able to pick out certain scenes were linked to certain VOCs. So there seemed to be an expression in the air. We're sort of reading emotions, if you like, out of the air by taking these sort of measurements. As a kind of spin-off to that, we actually used this database of films to actually be able to calculate the recommended age classification for unknown films too. So that's something we've also published if that's of interest to you. But that's kind of just the introduction of how we got into the indoor thing. One thing that we, of course, became aware of through these studies was that the real-world emissions from people are really rather large. As Alan said too, probably the main source in this room are ourselves. Okay? And in the real world, we were able to capture measurements of these siloxanes from cosmetic products, or from external. We were able to measure breath compounds like isoprene, and also ethanol, of course. If you've drunk beer or so, you're emitting it also into the environment too. So it's a real world situation. It's very high rates, and so we thought, okay, this is an important compound for indoor chemistry. We need to look at it under more controlled conditions and to really find out what a human being just living in a space produces for chemistry. And to do that, we took it out of the cinema and went to the more controlled conditions of a climate chamber, which is located in Denmark, run by the Danish Technical University. And so what we did was we basically ran an experiment with 4 people in a chamber under various conditions, which I'll describe to you in a minute. And that was part of this project, ICHEA, the Indoor Chemical Human Emissions and Reactivity Project, a Sloan-funded project. And what you see here is actually a rather unusual case. Normally, we would simply take 4 happy, healthy Danish students, put them in the climate chamber, and ask them to play with their mobile telephones for a few hours while we measured them. And in this experiment that you're seeing here, it's a special case. What we did there is we applied masks to the students so that we could separate what was coming from the skin and what was coming from the breath. Okay, so we could get like a separate measurement of both. So on the right, you can see the various measurement technologies we applied to this. And you can see they're all in sort of rather strange shaped racks. And these are flight racks because these measurement systems normally fly on a high-altitude aircraft and measure the very low concentrations that you get at the top of the atmosphere or in the stratosphere. And what we had was like proton transfer reaction mass spectrometers. We had a custom-made fast GCMS. We had an interesting new measurement to indoor chemistry called OH reactivity. I'll show you some results from that in a second. And on top of that, so kind of more standard stuff, ammonia, ozone, NO, CO2, methane, and of course some ultrafine particles. Now, of course, if we got a chamber, we can control the conditions. So we can run a series of experiments, each time with 4 happy, healthy students with fragrance-free washed clothes. We put them in there, and we run an experiment first without ozone and then with ozone. And we can vary the temperature just to see what sort of effect that brings, okay? With an idea for later recommending perhaps optimum ways of running your home, at what temperature, what relative humidity, etc. So we can vary the temperature, the humidity, the clothing, either shorts and t-shirt or long pants and long long sleeves. We changed the age. We had teenagers up to elderly folks in there, and we changed the ozone level, which is rather important. Okay, so here's some just data to give you an impression of how the experiment was run. And I have to say the data is still warm on the screen. We only finished the experiment 3 months ago, so everything I'm showing you here is kind of like a quick look direct from the measurement. And this is very much a typical experiment that's been done before. I think Richard alluded to this before. So this is, you bring the students in the morning, and they play with their phones for a while. And then in the afternoon, you put them back in, but put ozone on. And here I'm just showing you some of those classic ozone products which were mentioned before. The moment the ozone goes in, you can see that the products and the products of the products start to rise. And so we have data from the ozone side, but actually not shown here is a lot of the carbonyls, the alkenes, the acids, which we're normally emitting all the time, but they were also there. That's just to show you how the sequence works. So first without ozone, and then with ozone. And one interesting thing that cropped up was when we looked at the ultrafine particles. This was measured by a group based in the University of Lausanne in Switzerland. And they measured ultrafine, so we're talking like 1 to 2 nanometer size particles here. And under normal conditions, there was no real production of ultrafines. But the moment that the ozone was switched on, then suddenly we start to get ultrafines being produced around us, and they're growing in size up to sort of 2 nanometers. And that growth rate is strongly dependent on whether you're wearing t-shirts or shorts. Okay? So if you want to remember that, going home, think about Pigpen, the friend of Charlie Brown, as walking around with a cloud of particles around it, but you're generating particles around you all the time. Now, I talked about OH reactivity, and this is a technique This is a widely used atmospheric technique for outdoor chemistry, and we use it currently in our studies in the Amazon jungle. We do a lot of work currently deep in the Amazon jungle. And what we've done is we've developed a measurement method by which we can measure directly the total reactivity of the air. So in one direct measurement, we get a number for how reactive to the OH radical the ambient air is, and we get a number for that. And this is very handy because it allows you to do a budget and to find out how well you're doing at quantifying all the organics in the air. You can take that total number and you can compare it to the sum of the reactivities that you get when you sum up all the individual measurements that you've made times by their rate coefficient. And what you get is kind of like a budget that I've shown here as a pie chart. So you can say, okay, there was so much reactivity from all the measurables, isoprene, methanol, terpenes, etc. There was so much reactivity from the NO, ammonia, methane. But there can be a missing fraction. That was what we were after, to see if there was a missing fraction. And also to find out whether breath or skin was causing more reactivity indoors than between those two sources. So here's some sort of, again, rough data. This is not final correction, but it gives you the impression, I think, the first impression of the data. You can see in the morning, so the early morning section where we've got something like reactivities measured in per second, we've got something like 10 to 12 per second. In that period, there was no ozone entering the room, and most of that reactivity can be attributed to breath-borne compounds like isoprene, which is very reactive. Okay? But the moment you switch on the ozone, the reactivity leaps up factor of 3, and suddenly the air is becoming much more reactive to the OH radical. And it's also producing a number of compounds which are harmful and inflammatory to your lungs. So the message here is, with ozone, most of the reactivity is coming from your skin, ozone reacting with squalling and setting free very reactive compounds. But when ozone's not present, then most of the reactivity comes from your breath. And indeed, it makes a big difference to, in terms of temperature and relative humidity and clothing level. Let's look at the carbon dioxide and the ammonia traces here. This is, again, just taken straight from the field, these plots. And what you see with the CO2 is that quite rapidly, after the people enter the chamber, the CO2 sort of rises to a rough equilibrium. Okay? Now, the peaks that you're seeing there, they're deliberate. We actually encourage the students to occasionally stand up and jump around, just to move around, not get too bored, and see what happens. So those are those sort of spikes that you're seeing. And you see them in CO2, of course, because the breathing rate goes up, and also, to some extent, also in the ammonia, because the sweating rate goes up. But while CO2 goes to the walls, goes to equilibrium relatively quickly, ammonia seems to be just carrying on, adhering to the walls. So what that's telling you is that you, in the room, we are now all sending ammonia to all the surfaces in the room. Okay? And on those surfaces, of course, it can undergo interesting surface chemistries, which will hopefully be investigated by other people in this consortium. It makes a massive difference if you run your house at high temperature and you walk around in shorts and temperatures. It's like a factor of 10 more in the ammonia flux if you walk around like that in a hot house than if you walk in a cold house with long sleeves and long pants. And I should add maybe here as well, we also have another group that's actually taking measurements of the chemicals which are in those clothes at the end of the experiment. So there's sections of the clothing which have been worn by the students was sent also to analysis. So we not only measure the gas phase products, but also the products which end up finally in your clothes. Okay, so this is basically the take-home message I want to tell you, is that you have around you your own personal atmosphere, and you're emitting into it hundreds of volatile organic compounds through your breath and your skin. And when those volatile organic compounds interact with oxidants, be it OH radicals or ozone, they produce hundreds and thousands of more of these compounds. On top of that, we're strong emitters of ammonia that can go to the surfaces. They may interact with surface reactions. They may feed microbes on the surfaces. We emit a lot of CO2, 4% in our breath. Methane was also a strong emission, and interestingly enough, old people emit more methane than younger people. So that was there's a greenhouse effect for elderly people, maybe. The particle story is very interesting. We're looking at that very closely now to see if we can model, see if we can explain how we can produce these fine particles in the face of the large particles that are present. And of course, when these reactions are going on, you're generating a whole suite of radicals, Kriege radicals, OH radicals. And we've been seeing also in collaboration with Alan's group, I'm looking for Alan now, there he is, we've been seeing some very interesting effects between radical product abundances that are affected by relative humidity. And finally, I mentioned microbes because we're also a source of microbes, and the next speaker is going to tell us all about that. But the final message, the sort of take-home message I want to leave you with, is that we are observing very strong effects in terms of the emission rate of the volatile organic compounds, ammonia in particular. And so that means there must be optima that can be found in how you live your life to minimize your exposure. And that optima may change according to where you live. If you live in a hot, humid environment like Florida, or a dry, cold like Alaska. So there's an optimum to be found. And with that, hopefully I'm on my time. I just wanted to say thank you to the people who did all the measurements, particularly Pavel Wagoki and Gabriel Becker, who ran the chamber. Sarka's been doing the clothes stuff. Dusan's been doing the particles. Our team did the gas phase organics, and we've been having huge help from Charlie and Glenn throughout the experiment, and a very big thanks from the matchmaking of Paula and the Sloan Foundation for funding us. Thank you very much.